Scroll through any feed, and you're hit with a barrage of perfectly curated, flawless portraits. But the raw reality captured by a camera lens usually looks a lot more like this: a little crooked, a bit dull, and peppered with visual static. We expect our phones to instantly fix these flaws. But a computer doesn't actually see a person or a landscape. If you zoom in close enough, the subject completely disappears. To a machine, an image is a massive grid of dumb, flat squares. Pixels don't know what they're supposed to be. To turn that chaotic grid of data into something that actually makes sense to the human eye, the computer has to drag those pixels through a strict 3-part mathematical gauntlet. Every time you casually tap a filter, you are triggering an invisible cascade of algorithms working furiously to rebuild human visual perception from scratch. The very first step to fixing a crooked or badly framed photo is a set of operations known as geometric transformations. This chart shows exactly how that works. The algorithm alters the spatial relationship of the pixels on the X and Y coordinate grid, moving the original red squares from point A to point B. The actual color values of those pixels remain completely unchanged. For example, translation physically shifts the entire image by a specific distance across both axes, mapping the shape to the new coordinates labeled A', B'. Then you have rotation, which spins the data around a defined center point to fix orientation, and scaling, which applies a mathematical factor to resize the dimensions. If you've ever used a face filter on social media, you've seen warping. This maps pixels to entirely new positions using a localized function, stretching or squeezing specific areas without moving the rest. Together, these geometric transformations correct the spatial reality of the scene. They ensure the foundation is mathematically sound before a single color is enhanced. So the geometry is fixed, but the image might still be covered in digital static and noise. To clean that up, the computer uses morphological operations, which process the image based entirely on the shapes it detects. The core tool here is called a structuring element. Think of it as a mathematical magnifying glass, usually a small 3x3 matrix, that scans across the entire pixel grid, analyzing the squares directly beneath it. If it runs an algorithm called Erosion, the matrix actively shrinks object boundaries. It looks for tiny, isolated specks of noise that don't match the surrounding structure, and it eats them away. Dilation does the exact opposite. It expands boundaries. If the matrix detects a broken line or a fractured shape, it bridges those connections, filling in the empty gaps to create one continuous solid object. You can actually stack these algorithms. An operation called opening runs an erosion followed immediately by a dilation. This safely scrubs away thin, unwanted artifacts without ruining the main features of the image. Closing flips that order: dilation, then erosion. This is highly effective for filling in tiny, missing holes buried deep within a solid object. Forensic investigators rely on these same morphological combinations to repair impulsive noise and bridge the missing ridges on a scanned fingerprint. Morphology takes isolated, meaningless points of data and logically binds them into recognizable physical structures that a machine can actually understand and repair. We now have an image that is geometrically aligned and morphologically spotless. But if you take that perfect digital file and send it to a physical printer, the result usually looks completely wrong. That happens because the screen and the printer are using entirely different color models. These are the abstract mathematical frameworks that dictate how colors are combined and displayed. Digital screens use an RGB model, creating every color you see by adding varying intensities of red, green, and blue light. But a piece of paper doesn't emit light. It uses a CMYK model, subtracting light by mixing physical cyan, magenta, yellow, and black ink. This graph plots the full spectrum of visible human color, which helps explain the next concept: color spaces. Even among screens, colors will shift because each device has a specific color space, a rigid, defined range or gamut of colors it's physically allowed to use. A standard monitor used for everyday web browsing operates in the sRGB gamut, covering a relatively small triangle of that visible spectrum. But professional photographers work in Adobe RGB, a significantly wider gamut that captures a much broader range of intense, vivid colors. Without color spaces acting as a rigid translation layer, the exact same string of binary data would yield wildly different visual results on every single device we own. That raw, crooked, noisy file we started with has now been pushed through spatial geometry, scrubbed by morphological shape matching, and accurately mapped into a physical color space. The beautiful, flawless photograph you finally see on your screen is an illusion. It is a mathematical performance, sustained by millions of continuous, unseen microcalculations. Computer graphics algorithms act as the ultimate translators. They bridge the massive gap between a machine's cold, logical binary code and the complex beauty of human perception. So the next time you tap a screen to quickly enhance a photo, take a second to appreciate the intense mathematical labor happening right in the palm of your hand.